It takes some of it.
Okay, folks, we're going to go ahead and get started. So on Friday, I went over what I expected to be on the test. Today, I took the test and it took me 15 minutes. So that being said, if you know what you're doing, you have plenty of time. If you don't know what you're doing, you will not finish it. That's my experience. Because I don't, and it doesn't take me as long because I don't have to think through the steps anymore. I just automatically do them. And if you do it enough, that's how it becomes a second nature. So that is just, if you know what you're doing, you should have plenty of time because you've got 3 times longer than it took me. And my goal is usually 3 to 4 times longer. So you should be able to do it. But if you don't know what you're doing, if you have to think through every step, you may not make it. Now, I'm not saying you don't have to think through some steps. I'm saying you have to think through every single thing. you may not make it. So questions? Today, what I plan to go over is I plan to, number one, pick up where I left off on Friday. I figured out the error associated with the calculator that I had used, and therefore I fixed my program so that I can get the correct answer. Everything I did was correct up until the answer. And so I want to start where I left off on Friday, and then we're going to get into a Chattanooga principle. I am not only going to do now, as far as the problems from Friday, the last problem we did, not the quotient, reaction quotient, but the last problem we did where we were figuring out the concentrations of equilibrium. I'm only doing the one problem of that nature because it's not on the test. And we will be doing more of these, but we'll be doing it with acid-base equilibrium. So again, this is the only problem I'm going to do of this nature, just to give you insight into what's coming. But I'm not going to spend time doing extra problems of this nature. Because of the fact that it's not going to be on the exam Friday, and we will be doing plenty of them in the future. And that way also I can get to a Chattanooga principle, which is on the exam. Any questions? Okay, so on Friday, I had given you a problem where we had nitrogen reacting with oxygen to form two nitrogen monoxides. At 2000 degrees Celsius, this has a Kc of 0.10. The problem told us that we started out with 0.2 molar nitrogen and 0.2 molar oxygen, and that we had none of our nitrogen monoxide. As the reaction progressed, you would lose X amount of nitrogen, you would lose X amount of oxygen, and you would gain 2X amount of the nitrogen monoxide. These numbers are related to stoichiometry. So at equilibrium, we would expect to have 0.2 minus X molar of nitrogen. We would expect to have 0.2 minus X molar of oxygen, and we'd expect to have 2X nitrogen monoxide. So then you set up your equilibrium expression, and folks, don't skip the equilibrium expression step. I've seen a lot of people make mistakes simply because they skip the equilibrium expression step. So writing out the equilibrium expression, the equilibrium constant is equal to the nitrogen monoxide concentration squared divided by the nitrogen concentration times the oxygen concentration. Putting in all of our information at equilibrium, that means 0.10 for our equilibrium constant is equal to 2x squared divided by 0.200 minus x. I then went through the process of simplifying. So 2x squared, another common mistake is that people will square the x, but forget to square the number associated with the x. So 2x squared is equal to 4x squared. And then I used FOIL to begin to simplify the 0.200 minus x squared. And you get 0.0400, that's the first, minus 0.200x, the outer, minus 0.200x, the inner, plus x squared, the last. Simplifying that denominator comes out as 0.0400 minus 0.400x plus x squared. Multiplying through by the denominator, you get 0.004 minus 0.04x plus 0.10x squared is equal to 4x squared. I then rearrange the equation so that I set the equation equal to 0. And when I rearrange an equation, a lot of times I do rearrange it so that my x squared value is a positive. So when I rearrange this equation, 0 is equal to 3.9x squared plus 0.04x minus 0.004. You then use your quadratic equation, which I gave you the sheet that you could program your quadratic equation into your calculator. Our A is a positive 3.9, the B is a negative 0.04, and the C, I'm sorry, then B, let me redo that. The A is 3.9, the B is a positive 0.04, and the C is a negative 0.004. When you key this into the calculator, you will get out two possible X values. You will get an X X is equal to 0.0273 or a negative 0.03756. Now, only one of the X values will be valid. And the way a valid X value you will know it's valid if when added or when used in the concentration values at equilibrium, all concentrations come out to be positive. Basically, folks, you cannot have a negative concentration. The lowest you can go is 0. Because of that, the X value that we would use is going to be the 0.0273 molar. That's because the second value would have given you a negative concentration for the nitrogen monoxide. So again, only one is going to be valid. And in this case, it is the 0.0273 molar. Questions? Okay. So now what we're going to move on to the last topic in this particular chapter, which is Le Chatelier's principle. Le Chatelier's principle states, when a stress is added, to a reaction at equilibrium the reaction will move in a direction so as to alleviate that stress. Okay, possible stresses. Include addition of reactants, addition of products, removal of reactants, removal of products, the addition of heat. Well, let's say addition or removal of heat. The addition or removal of pressure in the case of gases. Gases are the only thing the pressure really affects. A change in volume. Again, as far as a change in volume, the only thing it really affects is gases. These are the most common types of stresses. So what I want to do, I think, is take each of these stress. By the way, these stresses, the first stresses, do not change the equilibrium constant. And these last stresses do not change the equilibrium constant. The only thing that can change the equilibrium constant is temperature. That is the only thing that impacts the equilibrium constant for a reaction. Hence the reason it's called a constant. The only thing that can impact it is going to be the temperature. Now what I want to do is I want to take each of these, the first six changes, or the first six changes, and talk about them. Actually, I'll deal with all of them. As far as what the change in it changes and the direction the reaction would proceed. Okay, if we add reactants, then the reaction has to go towards the products to alleviate the stress. If we remove reactants, we would expect the opposite effect. In that the reaction would head back towards the reactants. If you add product, then it's going to go towards the reactants. If you remove product, it'll go back towards the reactants. Remove product will go towards the products. Okay, let's talk about heat. It is going to be dependent upon what type of reaction you're dealing with. If you're dealing with an exothermic reaction where heat is a product, then if you add heat, you're going to drive it towards the reactants. But if it's an endothermic reaction and you add heat, you're going to drive it towards the products. Now, the opposite is removal of heat. Again, you've got to look and see, is it exothermic or is it endothermic? If you remove heat and it is exothermic, it is going to go towards the products. Whereas if it is endothermic and you remove heat, it is going to go back towards the reactants. I'm giving you this list because it's going to make your life easier depending upon how you learn. Some people like memorization work. This is going to be a memory work. Some people prefer to thoroughly understand it, and I'll illustrate how to understand it when I start working some problems. Okay, pressure. If you add pressure, the reaction will go towards the fewest gas molecules. And I'm talking about their number of moles. Remove pressure. And it'll go towards the greatest or the greater gas molecules. And finally, volume. If you reduce the volume, it goes towards the fewest molecules of gas. Whereas if you increase the volume, it will go towards the greater number of gases. Okay, let's start playing with a reaction. Now I'm going to not only, now you have the what it does, but now we're going to go into, I'm going to illustrate how you can determine what's going on. And the way I'm going to help you determine what's going on is we're going to play on a seesaw. How many people have played on a seesaw or seen a seesaw at least? Okay. Well, a reaction at equilibrium is kind of like a seesaw, where both sides are equivalent. When you disturb that seesaw, that's when the reaction has to move in a direction so it can reobtain equilibrium. So I'm going to illustrate using this idea of a seesaw. Okay, the reaction we're going to look at is nitrogen gas reacts with 3 hydrogen gas to make 2 ammonia gas. And this reaction is exothermic and has a heat that is produced of 22 kcals. We're going to have the stress. We're then going to look at which direction the equilibrium shifts. And from that, we're going to determine how it impacts the concentration of the nitrogen, how it impacts the concentration of the hydrogen, how it impacts the concentration of the ammonia, and finally, how it impacts the equilibrium constant. The first stress that we're going to do is we're going to add nitrogen. So again, we can think of this reaction as starting out at equilibrium. If I add nitrogen, then I'm adding to the reactant side. Now, if you think about a seesaw, that means that that seesaw is no longer going to be level. And our ultimate goal is to re-level that seesaw. So which way, if we're talking people here or masses here or whatever you want to call it, which way would something have to move in order to reestablish this equilibrium? To the right. Only if it goes to the right will it reestablish equilibrium. So we know that it's going to go towards the products. Now, because I added nitrogen, I really don't know how the concentration of the nitrogen changed. It could have gone, because we're adding nitrogen, but we're also shifting it towards the product. So the nitrogen may have ultimately gone up. It may have ultimately gone down. I don't know, because two things are happening to the nitrogen at the same time. We're adding it and it's causing it to go towards the products at the same time. But we do know that the hydrogen would decrease. We know that the ammonia would increase because we're going towards the products. And does equilibrium constant have it? Is anything going to happen to the equilibrium constant? No, because the only thing that impacts equilibrium constant is temperature. So it's the same. Or you can just draw a dash, however you want to do it, to indicate unchanged. Okay, let's remove hydrogen. Now what we're doing to our reaction that is at equilibrium is we're removing hydrogen, so we're removing a reactant. So which way will it have to shift to reestablish equilibrium? It's going to have to go back towards the reactants. If it's going back towards the reactants, we would expect an increase in the amount of nitrogen. Now, once again, we really don't know what's happening to the hydrogen, because not only are we removing hydrogen, but then we're shifting back towards hydrogen. So there's two things happening to hydrogen simultaneously. So we really don't know what's happening as far as the concentration. Now, if it's shifting towards the reactants, that means it's moving away from the products. And so we would expect a decrease in the products. And again, the equilibrium constant would remain unchanged. Questions? Okay. So let's increase the temperature. Okay. Temperature, if you look at this reaction, is a product. So if we're increasing the temperature, we're increasing the products, or we're increasing something on the product side. This reaction is no longer going to be at equilibrium. Which way must it shift? It's going to shift towards the reactants in order to reestablish equilibrium. Bless you. Bless you. Goodness. Okay, if it's shifting towards the reactants, we would expect the reactant concentrations to increase. If it's shifting towards the reactants, away from the products, what would we expect the product concentration to do? Decrease. Now, the last piece is, how does it affect equilibrium? We know that it affects the equilibrium this time because we're talking temperature. Well, the equilibrium constant for this is going to be the ammonia concentration squared divided by the hydrogen concentration cubed times the nitrogen concentration. To figure out how this shifts, let's just use some arrows here. We have said that in our K, the reactant or the numerator is going to decrease and the denominators are going to increase. So how does that affect our K? We would expect it to decrease because the numerator decreased and the denominator increased. So we would expect K to decrease. By the way, on my little arrows, you'll notice that I have a pattern that I use on these arrows. When I remove something, I will use an up arrow. When I add something, I will use a down arrow. The other thing that you will note about the initial equilibrium is basically that going from the first step to the second step, the arrow describes what happens to the teeter-totter. So on this last one, on the right-hand side, it had I increased the concentration, so it pushed that right-hand side down. If you look at the one before it, I removed a reactant, it pulled the left-hand side up. So in other words, the teeter-totter shifts in whatever direction you're pointing. And then it's always moving from the low end. So to go back to equilibrium, you always move from the low end to the high end. That tells you which direction everything is shifting. So this just gives you a little bit about how I'm using these arrows on the teeter-totter. They're telling a story. If I remove something, that side pops up. And then it has to go from the low end back to the side that popped up. If I'm adding something, I'm pushing it down. And it moves from that side that I pushed down to the higher side. So that just helps you with the little teeter-totter that I'm using. And until you get comfortable thinking of equilibrium as being basically a teeter-totter. Let's look at another example. Let's take the fact that 12.6 kcals of energy is added to hydrogen gas plus iodine gas to make 2 hydrogen iodide gas. Okay. So again, we're gonna have the stress. We're gonna look at its impact on the equilibrium. We're gonna look at the concentration, the impact on the concentration of hydrogen, iodine, and hydrogen iodide. And we'll go ahead and do the equilibrium constant. I'm going to give you three stresses, and I want you to predict what's going to happen to each of these. So let's increase the hydrogen iodide concentration. Let's decrease the temperature, and let's increase the iodine concentration. Okay. So if I increase the hydrogen iodide concentration, the reaction has to shift towards the product, towards the reactants. Because if I increase the hydrogen iodide concentration, I am increasing on the product side, which is going to cause the reaction no longer to be at equilibrium. So it has to shift towards the reactants in order to reestablish equilibrium. Since it's shifting towards the reactants, that means the reactant concentrations will increase. Again, because hydrogen iodine is being added and decreasing at the same time, I don't know exactly what happened to its concentration. So that's why I drew a dash. And then the equilibrium constant is unaffected because the only thing that impacts equilibrium constant is temperature. In the next one, I decrease the temperature. So basically I'm decreasing a reactant, removing a reactant. Since I am removing a reactant in order to reestablish equilibrium, I'm going to force the reaction to shift towards the products. I keep saying that wrong. I'm going to force the reaction to shift towards the reactants. If I'm shifting towards the reactants, that means the hydrogen concentration and the iodine concentration has to increase while the hydrogen iodide concentration decreases. Now, to figure out how it impacts the equilibrium constant, you've got to write the equilibrium constant, which would be HI squared over H2 times I2. And if you look at it, the hydrogen iodine concentration is decreasing while the reactants are increasing. So since you're decreasing the numerator and increasing the denominator, you would expect it to go down. And then finally, increasing the iodine concentration. Oops, didn't mean to do that one. If I increase the iodine concentration, that means I'm increasing a reactant. Therefore, the reaction is no longer going to be at equilibrium. In order for the reaction to reestablish equilibrium, it has to go towards the products. So if it's going towards the products, that means the hydrogen concentration is decreasing while the hydrogen iodide concentration increases. I don't know what happened to the iodine because I actually was messing around with the iodine. So I was adding iodine while the iodine was getting used up. So that's why there's a dash. And again, it doesn't impact the equilibrium constant. The last couple of minutes, I do want to show you what happens with increasing a volume or decreasing a volume? Because that was something that we haven't gone over. Just like we can talk about decreasing and increasing pressure. Okay. When you have volume or pressure, it's going to impact the number of gases. So go in and figure out, okay, I have 3 moles of gas on the reactant side. On the product side, I have 4 moles of gas. If I increase the volume, that means I'm going to expand. And if I expand, that means I have more room for gases. So it is going to shift towards the products in this case because I have more room for gases. Volume and pressure are related. If you go back to PV equals P1 V1 equals P2 V2 from Boyle's law back in college chemistry 1, they are inversely related. Meaning if I decrease the pressure, I'm going to what to the volume? Increase the volume. So again, it's going to go towards the products. Because again, pressure and volume are inversely related, according to Boyle's law. You didn't think you were going to have to use Boyle's law again, did you? Questions? Okay, that is Le Chatelier's, which we will be doing in lab tomorrow. And that is the last thing that will be on the test. What I go over Wednesday will not be on the exam. I don't know without looking at Le Chatelier's.